I'd like to pick up where we left off in the last video. So we had made a table actually in the last video, but it didn't have labels, okay? And so what we can do here is we can actually say, hey, we know that our first column of the matrix P is time, and the second one is population. So I could just say, well, time is equal to P, and again, this is supposed to be the first column, and I want the, let me get rid of this, we want the entirety of that first column, so we're just going to go like this. Okay. But I do want to point out, let's say we just wanted the, entries 3 through 10, then I could write in here actually 3:10, and that would give me just those rows 3 to 10 of the first column. Okay, but we want the whole thing, so this is all we need. And next we could go with population. I'll just leave it lowercase, population, and this was our second column. Okay, and then the next thing I'd do here is just write in table, and we could do time, comma, population. And it should be right down here in our command window, the table. Okay? Time, population, and I can of course pull it up over here as well. So let's see here. Let's go ahead and see if we can find our table. Here it is, time, population. And you can see all the corresponding times, corresponding populations. It's just those populations are written in scientific notation here. Okay, so next I would like to talk about actually graphing, and I actually want us to compare the solution that we would get from actually solving the differential equation versus what we found using Euler's method. I want us to plot both of those things. And actually, some of you might be noticing something new in my code. This thing right here that I'm highlighting. This new thing is the model that we would come up with had we taken differential equations, okay, and solved this analytically, okay. Now, again, you do not need to know how to solve this analytically. You only need to know how to solve this numerically. And by numerically, I mean using Euler's method. Okay. So no worries if you have no idea how we came up with the solution to the ODE here, okay, our ordinary differential equation. Okay. So the next thing I want us to do is to actually plot, again, these things. So let's start off with maybe just plotting what we found using Euler's method. Okay. And in order to do that, the first thing I want to do is let the program know what I want that x value to be. Or the x values. I should be a little more careful in the way I word that. Okay. And well, I want those to be all the things that are in the first column, and I want my y values to be all the things that are in the second column. And this should be enough here to plot it. Let's go ahead and hit run. Okay. And you can see here is our curve that represents that population, okay, as the years pass. Okay. Now, one thing that is a little confusing here is you can see on the y-axis here we do have actually this written in also scientific notation. Okay, but that's no big deal. And our bigger thing that I want us to compare here is this numerical solution. I want to compare it to the analytic one here soon. Okay. But I also want to show you one other thing. This line that you're seeing here, it happens to look smooth because we took 30 points in between 0 and 3 in order to plot this. So we actually plotted quite a few points. Okay. But had we plotted fewer, this actually might not look so smooth. Okay. And so just to smooth out your graph, you just need to plot more points. That's really it. Okay. Now, Another thing though is, since this really does consist of us finding a bunch of points and then the program plots, those points and connects them with straight lines, well, maybe we just want to see them points themselves. We don't actually want to see this connected with this continuous curve here. Okay? And so we can do that by going over here and hitting comma, and then we can put the asterisk there, and we want to put little quotes around it, and we'll go ahead and we'll hit run again. All right, and this can be helpful, especially if we're thinking about actually a data set, okay? And we actually just want to plot the points here. Okay? Now, there's a lot of different line styles, line colors, all that stuff, and luckily enough, MATLAB has a really great search function here in the upper right. You can actually see I've typed title into it recently. Okay? And the reason I think this is so helpful is it's pretty much impossible to remember every subtlety of a language. Okay? And so if, for instance, we are interested in, say, plotting something, and we want to read up on the documentation, we can just go ahead and hit plot here. And you can see here is what they're kind of telling us is that we have the option of just putting in X and Y, or we can put in X and Y with some other specifications. And there's some more options here. Like this next one down here is telling us you can actually use just a single plot command to plot multiple different equations here. So like X1, Y1 would be one curve, X2, Y2 would be the next curve, and so on. And then it's specifying if you want each one of those curves, you can specify more information about them. Okay? And one of the things that we added as an extra line spec here was we added in that asterisk. But there's more that can be done, and I want to kind of show you. If we go down here far enough, we'll find like there's a table of all the colors that we can use. Okay? If I get down here far enough, I'll find it. In fact, table of the different line styles too, if you want a solid line, a dashed line, dotted line, so on. And then what do you want those points to look like if we plot them, right? We did the asterisk, but additionally you have different colors here too that you can use, yellow, magenta, and so on. Not all of them are ones that you would immediately think of, like for instance, black is K here. So sometimes you actually will want to come look at this table. You might not remember, what letter to use for which color. Okay? And let's go ahead and there's a lot more information in here that you may not need, but if you're trying to really customize something, it can be really helpful to look through the documentation for the functions that you're trying to use. Okay? So I'm going to go ahead and I'm going to actually hit the X up here. And is what I'd like to show you is we can, I want us to look at the graph again, but then we're going to change the color of it. So right now it's blue, right? Well, let's make it red. Okay? We use R. Okay? So now we have red ones, okay? Which is fine. And if we don't want the dots and we just want to use a line or curve, we can just do this with R in between. And there it is, now it's red. Okay? But again, this was just our estimate, okay? So here soon we're going to add on to this the actual solution that we would get if we solved this differential equation analytically. Okay? So what we're going to need to do, though, is we want to take this inline function here and generate all the X and Y values that we need, okay? So let's do that. Okay. So for one, if I'm looking to generate a bunch of X values, well, how about we just say X equals, and we'll do F of, okay, and, actually I'm one step ahead of myself here. We're going to generate a vector of the X values first, then we'll do the Y values. I was kind of jumping ahead to the Y values there. Okay. So we're going from 0 to 3, right? But I want to use actually I want to try and stay consistent here. Since we spaced everything out by 0.1 with our Euler's method, you can see up here I have this I equals 1 to 30, right? And we said that h was 0.1. Okay. So yeah, we spaced everything out by 0.1. I'm going to do the same thing for this other one. 0, 0.1, and then we'll go all the way to 3. So this is just saying we're generating a vector that contains 0 to 3, and it's counting by 0.1 in between there. So it would go 0, 0.1, 0.2, and so on. Okay. And we can go ahead and suppress that. We don't need it. Okay. Now, before I actually input this, if you're ever going to input a vector into a function, you need to put these little dots here. And actually, let me get rid of them first because, yeah, you may not have expected those to be there. Okay. So the purpose of those dots is really so that we can plug the vector in here properly. Okay. And maybe I should actually go to a different window here for a second so you can kind of get an idea of what I mean. Let's just create a small vector here. How about 1, 2, 3, 4? Okay, keep it simple. Okay. Now, if I asked you, what is a squared? Okay. Well, I would expect to hear two answers. One is, well, you can't square a vector. That doesn't actually make sense. You can square a matrix, right? But we can't square vectors. That's not an operation. Okay. However, if you're wondering, is there a way that I can square every element of that vector? Yes, there is. And the way that you can do that is in front of your operation that you have here, you can put a little dot. Okay. And let me go ahead and I'll rename this something else. I'm not very creative with my names here. Untitled 12 it is. Okay. And you can see it did actually square each element of that vector. Okay. And then the next question is, well, what if we had maybe two vectors? Okay. What if we wanted to take the elements in one vector and divide them by the elements in the other vector? Okay. Well, let's see what that might look like. I'm going to maybe put in how about 4, 3, 2, 1? So in the other order. Okay. Well, I can't divide these vectors like normal. Again, that is not an operation that we have for vectors or for matrices. That just doesn't make sense. But if I want to take everything in A and divide it by the things in B, we can do that. Okay. And I'll just put a little point there, a little dot. And so now it did do that. You can see it did 1 divided by 4, 2 divided by 3, 3 divided by 2, and 4 divided by 1. Okay. So when we are working with vectors, it oftentimes, if there's an operation like multiplication or division or something like that, we need to let MATLAB know that we're trying to just do this element-wise. We just want to, like for this division here, we just wanted to do element 1 divided by element 2. Element 1 in this one divided by element 1 in this one. And then element 2 here divided by element 2 here, and so on. Okay. So that's what's going on over here in our logistic growth model, is we want to vectorize this. So this division here is slightly problematic because when I plug x into this function f, I'm going to be plugging a vector in here, which will create a vector, and I'm going to plug a vector in here, which will create a vector. But then the question is well, how do you divide two vectors? Okay, and we can't. We just want to divide them element-wise. So I'm going to put a point here. Okay, and I think that's all I want to say about that. Let's go ahead and try this out now. So we have our x values. Let's also compute our y values. So y should be equal to f of x. Okay. So all this is going to do is it's going to take our vector x and it's going to plug it into our function f, and it's going to generate a bunch of y values for us that we will then be able to plot. Let's just hit run now before we actually try and make the other plot. I just want to make sure that I don't have any typos anywhere here. I want to make sure I don't get any error messages. So I'm going to hit run real quick. Okay. And no error messages, so I'm happy. Okay, let's put the second plot on there. So if, for instance, we want to put both of these plots on the same set of axes, we can hit hold on, and then we can hit plot. And then we can say, hey, we want to plot those x and y values that we just found. Okay. And now remember, these x and y values that I'm about to plot, these are from the original, not the original, these are from the analytic solution, the thing we would get if we were actually using, calculus to solve this. Okay. But we used Euler's method. And so we're going to compare these two solutions. And here in a minute, we should see that they're very similar. Let's make this one in blue. Okay, and you can see these two things are very close, and you could zoom in. Okay. But you can see our solutions are very, very similar between what we got using Euler's method and what we get analytically. Okay. But now let's say you want maybe a legend on here. Well, that can be done. We could say, hey, we want the legend to first say, I'm going to give us 2 spaces here to fill in stuff. So the first thing that we plotted, we want the legend to let us know that that first plot is, that was using Euler's method. Okay. And the second one was the analytic solution. And we can go ahead and hit run. Okay. And now it's letting you know, hey, this red line is the one we got using Euler's method, and the blue one is the one that we got using the analytic solution. Okay, but we can add more. We can add titles, and we can add labels to the x and y axis. So I can go in here and I can say, hey, that x label, it should be years, and our y label, this should be population, and I can go ahead and hit run. Okay. And you can see we have population on the side, years on down here, and if we want on top, we could give this a title. What do we want to title this? Just for the sake of simplicity, we were studying deer here. How about I just say deer? Okay. Okay, it looks good. Okay. But now, maybe you want to present this material in a different way. Maybe you would like to have both of these graphs separate. Okay, both of these graphs separate. Well, then you can use actually the subplot command. And I'm going to show you how that works. So when you use the subplot command, the first thing that you want to think about is how many things are you actually trying to plot? Okay, are you trying to plot 4 things, 2 things? Well, for us, it's just 2. Okay, and so we have a choice when we plot 2 things. We can either stack them one on top of the other, or we can put one on the left, one on the right. Let's go with thinking about this horizontally. Let's do one on the left, one on the right. Okay. And so if you think about that almost as like a matrix or a grid, this would be a 1 by 2 grid. So I'm going to do 1 by 2. All right. And I'm going to do the same thing right above our other plot. And I haven't finished the subplot command. I'm just pointing out that these first 2 entries are just letting us know what are we going to break our grid up into, okay? And we've broken it up into a 1 by 2 grid, okay? And now it counts these, each location in the grid, it just counts using a number. So the first location in our grid we'll call 1, and the second location we'll call 2, Okay? And if this was a bigger grid, there might be a third and a fourth and a fifth location in that grid. Okay? And if you ever forget how to count the things in that grid, remember this documentation up here is pretty awesome. You can type in subplot and it'll tell you how to actually count when you're using this subplot command. Okay, if you were going to do something more complicated. Okay, and before I go any further, I think I want to get rid of some of this for a moment. Let's see. I'm going to get rid of the legend, but I want I'm going to want both of our plots to have actually the same. I'm going to put a little bit of space in between some of these things so we don't get them all mixed up. So we're going to want the same X label and Y label on the two graphs that we're about to make. So I'm going to put them in on both of these. Okay. And I actually, next, let's check and see if we even need hold on now that we're using the subplot command. We might still need it. We're going to find out. But I'm going to get rid of the titles. So all we really have here so far at the moment is we have our X and Y labels, and we're going to plot both of these, and you'll see that the first one should be our solution from Euler's method, and the second one should be the one from our analytic solution. So let's go ahead and hit run. Okay, and there they are, and they look very similar just like they did before, so no surprise there. And so yeah, you can see we actually did not need hold on now that we use the subplot command because we're doing something a little bit different here. Okay. But maybe we could label these now and give them both a title. How about we give them the same titles that we actually used when we were using the legend. So how about title, we'll go Euler, and we don't want to forget, put those little apostrophes on each side, and we'll want to do the same thing here for this one, title. And is what we could do here is call this one analytic, and we'll go ahead and we'll hit run, and there it is.